let's kind of put together the idea of integrals and being able to estimate integrals using the left-hand and right-hand rules. So we have this function. So we have a quadratic 3x squared plus 2x plus 1, and we're bounding it by 1, 3. And we're going to supposedly break this up into 4 subdivisions or 4 partitions. And from that, we're going to do 6 different operations, some of which are easier than others. We're going to sketch the graph. That's easy. We're going to calculate delta x in the grid points. That's easy. We're going to sketch the graph using the left-hand Riemann sum endpoints, and we're going to approximate or determine if it's an under or over estimate. That's going to be pretty easy. We're going to do the same thing with right hand, but then the most difficult parts, or the most taxing parts, is being able to actually compute those left-hand and right-hand endpoints using the Riemann sums. All right, so let's get to it. Sketch the graph, okay? Really nice quadratic, all right? To be able to do this, you could just put in your graphing calculator, all right? And I'm just going to exaggerate what this looks like. Now, I know that if I plug 1 in, which is the lower bound, all right, that's going to be 3 plus 2 plus 1, which is 6. So 1 point, if I were to graph this, like really small, I'm going to get rid of this Y marker. All right, that's going to be right about here. Okay, so that's the 0.16. All right, now the other point, and this is x equals 1. If I have x equals 3, we'll call this x1 and x2. If I substitute 3 back in, that's going to be 27 plus 6, which is going to be 33, and then 34 is going to end up being the highest point on this. So somewhere up here, and we have the quadratic sort of curve on this. All right, so this is about what our function looks like. All right, of course, you could just throw in your calculator. Okay, and again, that's the point 3 comma 34 if I did all of my computations correct, which I hope I did. All right, so 4. All right, so given that information, all right, now we can go ahead and do the second part where it asks us to compute delta x, okay, which should be pretty easy, and then also to be able to find the grid points. All right, so delta x is found by the formula b minus a over n. In this case, a is 1, b is 3, and n is 4. So that's going to be 3 minus 1 over 4, which is going to be 2/4 or a half for delta x. Now, to get to the grid points, all we're going to do is we're just going to partition this, and we're just going to add 1/2 each time. Okay, and we're going to be able to get to the next grid point for this. Okay, so we know that x0 is 1, that's or a, and then if we just add a half to that, it's 1 plus a half, which is going to be 3/2, and then x2 is going to be 3/2 plus 1/2, which is 4/2 or 2. And you can see how this is going to go. So it'll be 2 plus a half, which is 5/2. And then finally, and not surprisingly, we should get 3 because that's our terminal point. Okay, so 3 is our terminal point on our domain. All right, so delta x is a half, and then these are the grid points. Okay, so 1, 3/2, 2, 5/2, and 3. All right, now sketch the graph using the left Riemann sum, and then determine if it's an under or an over estimate. Okay, so once again, we're just going to sketch the graph. All right, and remember our graph looks something like this. All right, so this is 1. I'm going to call that like x0. All right, and let's just call this x4, which is 3, and I'm calling it x4 because that's what we got here. And what we're going to do is we're just going to draw these rectangles. Okay, so there's one rectangle, and we're using the left endpoints. Okay, and then here's another one. And then here's another left endpoint. All right, and then finally, here's our last left endpoint. All right, now notice there's a lot of underestimating. Okay, so there's like a hole here, and a hole here, and a hole here, and a hole here. All right, so those are all underestimates, okay, because of the holes that exist underneath the graph. All right, so this is an underestimate. all right? And let's just have these points where we had x1 was 3/2, x2 was 2, and then x3 was 5/2. Now we need those because when we compute the Riemann sum, we're going to substitute these values back into the function. Remember that the delta x is a half, which means that the base of each of the rectangles is a half. So this is a half, and this is a half, and this is a half, and this is a half. Okay, so no matter what, the base is a half. So for the first rectangle, that's going to be 1/2 times the function, the height of the function at 1. And then for the next one, it's going to be the base times the height. And this times is 3/2. So all we're doing is we're just going to evaluate the function at each of the different partitions of the left endpoint. So we have 2, and then finally we have 1/2 function at 5/2. All right. Certainly we could factor out a half and make this a lot easier on ourselves. So 1/2 f at 1, f at 3/2, f at 2, f at 5/2. All right. And now what I'm going to do is I'm either going to punch this in the calculator, or I can use Excel to make this a little bit nicer for myself, because we are doing sort of repetitious computation. Now remember, the function was 3x squared plus 2x plus 1. All right, so what we can do in Excel, I'm just going to drag my Excel screen over here. I'm going to put in the delta x's. So 1, 3/2, and then 2, and then 5/2. Of course, we could just get the decimal approximations of those. And so remember, we had 3 times x squared, but instead of x, I'm just going to use a1 squared because I'm referencing this 1 here, plus 2 times x, or 2 times a1 plus 1, right? So that gives us 6, which is the value of f at 1. I'm just going to take this box and I'm going to drag this down, and that gives me all of the values. So this is f at 1.5, f at 2, f at 2.5. And then finally, I'm going to add these up by using the function equals sum parenthesis. Right? So 58.5 is not the area, but it's the sum of the functions at the left endpoint. Okay, so we're going to take a half of that 58.5. All right, and I'm just going to use Excel once again for that. So I could just say equal 0.5 times 58.5, or I could just use my calculator, 29.25. All right, so, and again, that's an underestimate of the area, okay, by using the left endpoints. Now let's use the right endpoints this time, okay? So now we're on the part E, where we're going to sketch the graph using the right endpoint, determine if it's an under or an overestimate. Okay, so here is our graph. All right, so this is x equal 1. Here's our graph. Here's x equal 3. All right, and that's good enough. Okay. Now using the right endpoints, right? Let's do this. Do this. Okay. And remember, this was the value right here of, I call that x1, call that x0. This was 3/2. And then here's another right endpoint. Okay, so this was x equal 2. All right, here's another right endpoint. All right, so you can clearly see these are endpoints. And then this is our last endpoint right here. And if I call this x2, x3 was 5/2. Now, here's the good news. We can recycle what we just did, except remember we had this was one of the endpoints. We're going to get rid of that, and we're going to use 3 instead. So realistically, I'm just going to go back up here. I'm going to get rid of f at 1, and that's going to change this. And I'm just going to replace that with f at 3 to make it really nice on myself. Okay, so I have 3 here, 3, and I'm going to go back to Excel. And this is really cool. Instead of having 1, I'm just going to change this to 3. Right? And notice it changes everything for us. So remember, we had 1 here, it was 6. Now I plug in 3, 34. And I'm going to take half of that 86.5, and I get 43.25. Okay, so this was 86.5, and then the right area, or the right-hand area, 43.25. Now, one thing that we forgot to do, and this was part F, this was actually the second part, estimate the integral using the right endpoint. But one thing we forgot to do, or I forgot to do, was to label this as an overestimate. And I think everybody can see that from the diagram. We get all this area that's above the curve. Okay, so these are all overestimates. Realistically, the area falls somewhere between, the actual area is going to fall somewhere between the left and the right endpoints. Okay, or the left and right area that we approximate. So remember, we got 43.25, and I think it was like 26 or something, 29.25. All right, so the real area is somewhere between there. All right, and in the next series of videos, we're going to look at the fundamental theorem of calculus as to how to get that exact value. Okay, but for right now, we're just approximating using left and right endpoints. So we're going to do one more example like this in the next video, where we do some trigonometry next time.